So this would be our last Zoom lesson, the last video of this course. Today we're going to focus on some problems I made them up and I worked them out. They're very similar to two things. The first thing, they're very similar to your homework assignment. Then the second thing is they're going to be very similar to the problems you have on the final exam. As you know, your homework assignment is due, I believe I said Thursday, next Thursday at the end of the day, 5 p.m. And the final exam is a week from Tuesday, May the 5th, starting at 8 o'clock. And I will email you the exam package a little bit before 8, and I need it back by noon of that day. So if I get any of these dates wrong or you have any questions about them, give me a call, text, or whatever. So let's get started. All right, so I need to pull up, here's the homework, and I gave you a copy of this, by the way. So I need to make sure I share the screen. Oh, goodness. Let's see. Take me a little. Okay, share, see, share, see what you've got shared. This always gives me a little trouble, as you know. Okay, that looks good. Now, share that. And I want to bring up the tables. So we'll be using the tables. I'm going to put my picture down here somewhere out of the way, maybe over here. Okay, so we're ready to go. Again, these problems are very similar to, oops. Okay, here's problem number one. All right, I'm gonna check share one. I got a paranoid about making sure this share, it looks like, okay, you're good, you're good. Okay, this is problem number one. If you look at this schematic here, you see this is a Rankine power cycle. It has the four elements of the power cycle. It has the turbine, produces the work to drive the generator. It has the condenser, which takes the low pressure, hot, mostly vapor out of the turbine after it's exhausted most of its energy or a lot of its energy, and condenses it, turns it into liquid water. And then it goes, and this is all at low pressure. It goes through the pump, and it's pumped up to the high pressure of the boiler, where the heat input to the boiler is. This heat input can be cold, nuclear, even solar heat. And it produces steam at a relatively high pressure and temperature, and ready to go through the turbine. This process continues. So let's read the problem. It says the Rankine vapor cycle shown in the figure to the right is designed to produce 22.2 megawatts of electrical power operating at the conditions shown in the figure. So that means this output right here is 22.2 megawatts. Analyze the system as outlined below. Complete the table of enthalpies for the table shown on the next page. Let's see. Here's the enthalpies. We'll get to those. Right. Analyze the steam turbine to determine the mass flow required to produce 22.2 megawatts of output power. That's the mass flow flowing around the cycle in kilograms per second. Determine the heat transfer into the boiler in megawatts, it's QN. Determine the power required to drive the pump. There's external electric motor required to drive the pump. And finally, what you're looking for is the overall is determine the thermal efficiency of this entire cycle. So I don't know if I said draw the TS diagram, should have, but here it is. So let's take a look at this. We're dealing with water, which is used as steam, which in a cycle is, we heat it to produce steam. That's where we get our power. And we also have, well, we have it in all three phases. We have our three conditions, two phases. We have water, we have steam, which is superheated vapor, and then we have a mixture of vapor. So what I'm getting at is you need the dome. So we draw the dome in. Now we know the high pressure, we know that a Rankine cycle is essentially bounded by two pressure levels. High pressure inside the boiler, and that's going into the turbine, and the low pressure, which is the condenser into the pump. So we're given up here that our high pressure is 80 bar, so we draw our 80 bar constant pressure line. And by the way, this temperature entropy diagram. So now we know our low pressure. We look down here, the pressure coming out of the turbine, which is constant going through the condenser, is 0.08 bar. So 0.08 bar, we draw our low pressure line. So we're well on our way to having this thing drawn out. Now we look and let's see what the pressure coming into the turbine is 80 bar and 400 degrees. Well, here's the 80 bar line, and it intersects at 400 degrees, somewhere like this. Now, by the way, the temperature through here is 295.06 degrees. You can look that right off the saturated table. So the pressure and temperature are dependent through the dome. Then when we go out here, the temperature increases. So we're at 400 degrees. And we choose this point on our little sketch because we know when we go constant isentropic expansion that we're going to hit down here somewhere at about 85, 90% quality level. So we want our diagram to look reasonable. So this is the isentropic expansion through the turbine from the high pressure to the low pressure line. Excuse me. Constant or isentropic. Now here's the actual expansion. We know the entropy does increase. And we suspect it's going to be out here still quality, not out in the superheated zone, but about right in here. So now we know when we get to here and we go through the condenser, we come out of the condenser at state 3. By the way, turbine was 1, isentropic to 2s, actual expansion process ends at state 2. State 3, we know is saturated liquid, so we know we're at that point right here. This pressure, saturated liquid. And by the way, we can look up on our saturated tables and see the temperature here is 45.41 degrees. And I would want you to show that. Of course, this pressure all the way out here is 0.08 bar. Sorry. So now we go through the pump. We got to pump this liquid water up from a pressure of 0.08 bar up to 80 bar. And the ideal pumping process, just like a compression process, is isentropic reversible, adiabatic. And so we have this straight line up from this pressure line of 0.08 straight up to 80 bar. And the actual pumping process, we know increases entropy, so it looks something like this. And then I draw in my little S equals C to show that that's isentropic and that's an isentropic. By the way, these lines should be straight across. They're not, they're slanted a little bit, but anyway. So let's get the enthalpies. All right. So H1, I don't believe I showed it down here. I had forgotten. H1 is just H at 80 bar and 400 degrees C on table 933. So let's go over here and look at table 933. All right, so we go down to the 80 PSI mini table. 80 bar. Oops, got away from me, didn't it? 20 bar, here's 80 bar. 80 bar and 400 degrees C. Here's the mini table at 80 bar, which is also 8 megapascal. 400 degrees C. So we look over here and there's H1, 3138.3. And there it is, 3138.3. Now, here comes the part that all of you missed on the test. I want to explain it to you. Well, if you look back at the problem, you're given the isentropic turbine efficiency is 90%, but you're not given much about the state 2 except it's 0.08 bar. You don't know a lot about state 2. But now your approach here is you can look up / calculate H2S because you know the entropy is constant for the H2S state. So let's look up. By the way, we looked up S1 when let me go back to that. Here's the 80 bar, 400 degrees, S1, 6.3634 kilojoules kilogram K. There it is. So we know S2 is equal to that. So we want to find H2S, which is a function of S2 is 6.3634 and P2 is 0.08 bar. So that's what we know about state 2S. Now, let's go back to the saturation tables because I have a strong suspicion here that we're going to be in the mixture zone, which the saturation table will give us, with a quality of maybe 85%. So let's see if that's true. So I know I'm at 6.3634 entropy and 0.08. So let's go back. We're getting there. There's 0.08 bar. Now let's look at the entropy. SF is 0.5926. That's the S at this point. SG is 8.3304. That's the S at this point. Our actual S2, which is same as S1, is 6.3634. So we know indeed we're between those two limits. So we have a quality, a mixture, and we need to calculate the quality. Once we calculate the quality, we can use the quality equation to calculate the enthalpy of H2S. All right. So, like I said, we know that our actual entropy is greater than SF. That's less than Hg at 0.08 bar. So it's no state 2 is a mixture. So we can calculate X2S as S. That's actually S2 minus SF over SG minus SF. And if we put those numbers in, okay, S is 6.3634. There it goes. SG 0.08 is 0.64. I'm sorry, 1, 2, 3. 0.5926. There it is. SG is 8.2287. There it is, minus SF. which we already pulled up. That's on page 929. So we calculate X2S is 0.7557. We want to keep that at least 4 digits, not chunk that in memory location 8. So now I know X2S. So now I can use this same equation only with H in it, which is absolutely correct, to calculate H2X. H2S, and H2S is just equal to HF plus X times H of G minus H of F, which is for enthalpy only now, is given as F of HG. It saves you a calculation. So let's look. Here's 0.08 bar. Here is HF was 173.88. So we solved this equation for H2S is, well, I mentioned that. So here's the 173.88 right here. And I could put right here as HG minus HF. But since I have HG already, H of FG already calculated, why not use it? So it's 24.3.1. So then I go through this little simple calculation and I get 1990.0 is H2S. And I use the same amount of decimals and digits that I have in the table, which is 4 numbers and 1 decimal, 1990.0 kilojoules per second. There it is. So now we have X, we have H1, we have H2. By the way, I meant to say, when you get all these enthalpies done, you pretty much got your problem solved. Now we need to get H2. We got H2S, we need H2. So now we use the isentropic turbine efficiency equation. Is the isentropic turbine efficiency is equal to H1 minus H2 or H1 minus H2S. We're given the isentropic turbine efficiency is 90%. Let me make sure that's right. 90%, there it is right there. So now we just solve this equation. Just be careful and solve the equation for H2. That's the only unknown right here. And you get H2 is 21,902,109.3. Again, using the same number of digits and 1 decimal point. Plop it in. Now we've got 3 of the enthalpies. We're on our way. Now enthalpy number 3, H3, is a gimme. It's just saturated liquid at 0.08 bar. So let's go over here to our saturated table. 0.08 bar, and we're looking for HF. 173.88. There it is right there. So that was a gimme. But H4 and H4S are not gimmes. They've got to have some calculations. And let me see. H3 is going into the pump and H4 is coming out of the pump. Now going into the pump, you know H3. Going out of the pump, all you know it's 80 bar. You know it's a liquid, and you know it's 80 bar. And you could look up H4 based on the pressure of 80 bar and it being a liquid, but you might not get a very accurate number. And the best way is to do it like I'm going to. And I don't think we've done this before, so you need to listen up. So let's consider the pump. We know the work of the pump per pound is H3 minus H4. Now I know your book gives H4 minus H3 because the author of the book wants to keep everything positive. If you want to do it that way, that's fine, but you got to be really careful. And I would suggest you keep your signs like I've got them. Work of the pump per pound is H3 minus H4. Now, there's also another equation we haven't used much that we're going to use now. Since this is a incompressible fluid, essentially, liquid water, we can use the equation that the work of the pump isentropic per pound is equal to V dP. And I could go through the derivation of that, but on this board here, it take us a half a day for me to get the writing. But take my word for it, it's perfectly accurate within a percent or two to say the work of the pump isentropic is specific volume, and we know the specific volume at state 3, we're going to look it up, times dP, which is just P3 minus P4. So specific volume at 3, we look it up, it's 1.0084 times 10 to the minus 3. All right, let's look at that. Here's 0.08. Here's specific volume, 1.0084, but you've got a 10 to the, they show it a 10 to the positive 3. What they're saying is, if you take the specific volume and multiply it by 10 to the 3, you get this. So what that means, and think about it, that means that the table value should be 1.0084 times 10 to the minus 3. If you don't get that, just put in a 10 to the minus 3. But be sure you pick that up. So there's the specific volume in cubic meters per kilogram. Now the pressure, P3 is very low, 0.08. P2 is 80, and these are bars. A bar is 10 to the 5th pascals. A pascal is a Newton per meter squared. So I just put in these numbers in bar times 10 to the 5th Newtons per meter squared. Now remember that a kilojoule is 1,000 Newton meters. So I put this in. And my answer is going to be, and the answer I'm looking for, kilojoules per kilogram. So the work of pump isentropic is 8 minus 8.062 kilojoules per kilogram. So I'm going to back in to find H4S. I'm going to back into it. I know what H3 is. It was a gimme lookup. I've just calculated isentropic work using this formula VDP. So now I can just, with simple calculation, and make sure you keep your signs right, I get H4S. And remember, it's got to be bigger than H3 because it's a higher pressure, higher power level. So H4S is equal to H3 minus work of the pump isentropic, which is a minus. So minus times a minus, and I get a plus. And I get H4S is 81.94. So I've sort of backed into that, but that's the way to do it. It's perfectly legit. Now I know H3 and H4S. I know the isentropic pump efficiency is 80%, by the way, which is customary. That's a very realistic number. So now I can use my isentropic pump efficiency equation is H3 minus H4S over H3 minus H4. Or if I want to use what's in the book, I can turn these around. H4S minus H3 over H4 minus H3, doesn't matter. You get the same answer. So the only unknown, I know H3, I know H4S, I know H3, I know eta of the pump isentropic. So only thing unknown is H4. So I solve for H4. By the way, H3 was saturated. Oh yeah, I showed you where I got that. I just stuck this down in here to remind me. So solving for H4, I got 189.96. And if I look at my table, now my table is complete. By the way, for page number on these, I just put I calculated. Now it's possible I've calculated one of these wrong because I don't have any way to, I don't have it, I made up these conditions, so I don't have an answer. So if you go through the calculations and you get, say, a different number from one of these 3 enthalpies, actually I calculated 4 places, right? 2S and 2, 4 and 4. If you get a different number, you may very well be right. So don't just check it over. If you're convinced you're right, you probably are, because I do make mistakes. So now I've got all the enthalpies and I can start calculating. The first thing it wants is what's the mass flow rate, and I put a W for water. So I write the energy equation about the turbine control volume, which is this right here. Remember, I got the work coming out of it. I got state 1 coming in, state 2 going out, and the work of the turbine coming out. So just got to be really careful with units, because I'm solving for the mass flow rate. I know the power out of the turbine is 20. Well, here's the equation. Now, you know the equation usually has H2 minus H1 equal minus W. I just got rid of the minus on the right-hand side, and this is what you'll get. Now, I got 22.2 megawatts times 1 times 10 to the third kilowatts per megawatt. In other words, there are 1,000 kilowatts in a megawatt. Down here's the enthalpies, and they're in kilojoules per kilogram. And a kilowatt is a kilojoule per second. Now I put the second back up here. It just helps me make sure I got everything right. But the kilojoule per second, seconds down under here. I just put it up here. And go through my calculations, and I get, it may not be right, I think it is, 21.4 kilojoules per second. Actually, I calculated 21.380, and I store that in memory location B to use later to maintain accuracy. I don't use this in subsequent calculations. It doesn't have the accuracy I need, so I drop back and use this number. But this is the answer you box to 3 significant digits. All right, 3 significant digits. So now the next one asks you to calculate the heat in to the boiler. And that's just M dot, which you calculated here, times H1 minus H4. Go through the calculations. And I get, and I got this number, 63.164 megawatts. Oh, that should be kilowatts there. 63,164 kilowatts is equal to 63.2 megawatts. Hopefully I didn't. That should be a decimal, 63.164. Okay, all right, very good. Now, what do I need next? I need the work of the pump. Well, I know what the enthalpy change is, H3 minus H4. So I just multiply by the mass flow rate. By the way, that mass flow rate, as you know, flows all around the cycle. And I get work of the pump actual is minus 0.172 megawatts. That doesn't sound like a lot, but that's 172 kilowatts. That's a pretty good amount of work, but it's just small compared to the output of the turbine. Now the turbine, as you know, doesn't drive that pump directly. The pump is driven by a separate electric motor. And if you don't get this minus sign, I'm okay. I'm not going to count off on it in final, but remember, now you're going for the thermal efficiency, and I like to use plus and then let the signs take care of themselves. But if you just make sure that the big number here, that the smaller number is algebraically subtracted from the larger number. This is the work of the turbine. This is the work of the pump. You do not add them. They do not combine to get a bigger number. They combine to get a smaller number. And if you go through these calculations, you get the work of that cycle, or the efficiency of that cycle, 34.874. This is in percent now, 34.9%. So that's the pretty good analysis of the Rankine cycle here. Here's the TS diagrams. You need to be able to draw and understand that diagram. If you cannot draw and understand this diagram, you need to call me. I might not can take your call right then, but I'll call you back. Because I don't want to, I'll be honest with you, I don't want somebody coming out of this course and not being able to draw, whether you make a B, C, or D. I don't want you to come out of this course and not understand this diagram and this circuit. All right. So that's our Rankine cycle. Sort of the interesting thing about it, we got a decent thermal efficiency of 35%. Pretty decent number. It's a good number, actually. Now, just because that looks fairly low compared to some isentropic efficiencies, that doesn't mean that's not a very economically viable process, because what you're doing, you're putting pretty low, inexpensive heat into a boiler, and you're getting about 35% of the heat in out as good quality shaft work. So that's, economically, it's probably costing you 3 or 4 cents a kilowatt to produce that electricity. That's the gross profit. Of course, you've got other things that will come out of that. But so that's a really good process. The problem with it, of course, is the global warming impact it has because of the coal. That's why I'm a big proponent of nuclear power. I don't want to get political here, but in my opinion, we'll never get to all electric cars. We'll never get rid of fossil fuels until we realize we're going to have nuclear power. Now, it has to be done safely. I totally agree with that. All right. So now let's go to the next problem. This is the Brayton cycle. This uses air, just regular old air you breathe, pulled into a compressor, goes through this heat exchanger where it's mixed with a small amount of fuel, generally natural gas. It's combusted in this heat. This is actually a combustor. I should have changed. It is a heat exchanger, yes, but I should have changed that name to combustor. And then it goes to the turbine. Now we use the ideal gas equations for air through the whole process, even though there's a little fuel involved in here, and after the combustion process, there's some different chemicals formed. But believe me that the properties of this process after it's combusted is very close to ideal gas of air, and the air analysis is strictly straightforward and accurate. But let's look at this circuit. So we bring in air. We could bring it in for this heat exchanger or bring it in directly from the atmosphere. It's pretty much atmospheric conditions. You see it's 1 bar and 300 K. That's the atmospheric conditions. Goes through the compressor and it's compressed up to 12, what's that, 120 bar? Let's see, 12 bar, I'm sorry, 12 bar. Just multiply, move your decimal place 2 places to the left. So 100 kilopascals is 1 bar, 1200 kilopascals is 12 bar. And then we go into a heat exchanger. That's where we combust it, add in the gas, ignite it, and we get a lot of heat added right here. Instead of a boiler, we're putting in actual natural gas and igniting it. Then it goes through they call it a gas turbine, and we get shaft power out. Now the shaft power has to go 2 places. About half the shaft power goes back to drive the compressor. And about half, and we'll see the exact percentages later, is free to drive the electric generator. All right. So we have, we know P2 is 12 bar, P3, we go through this heat exchanger at constant pressure is 12 bar. But our temperature goes up immensely. Now, we don't know what T2 is, and I don't think we even have to calculate it. It's probably somewhere like 700 or 800 degrees K. We know T3 is 1400 K. We don't know what T4 is, but we know P4 is back down to the low pressure of 100 kilopascal, or 1 bar. Now, we do know the compressor efficiency, isentropic efficiency is 84%, and the turbine efficiency is 88%. All right, let's read the problem. The gas turbine power generation cycle shown to the right operates in the Brayton cycle, named for who? Mr. Brayton, right? The net power output of the turbine used the net now. Some of it goes here, and what's left, the net, is free to drive the generator. The net power output of the turbine used to drive an electric generator is 45 megawatts. With this information shown in the figure, perform the following. Look up and or calculate the enthalpies required to complete the table on the next page. Actually, the table is on the same page. Sorry about that. Then compute the power to drive the compressor. Compute the heat transfer in the boiler. Compute the thermal efficiency of the cycle. And determine the back work ratio, which is just the ratio of the total. I believe it's the ratio of the compressor power to the total power of the turbine. I believe it's the ratio of the power the compressor requires over the total power the turbine produces. We'll see in a minute. All right. And I don't believe I said draw the TS diagram. I should have. Okay. But draw the TS diagram. You'll have to do it on the final exam. Now, here's all I'm looking for on a Brayton cycle. You've got two. Now, I don't want to see a dome. This is an ideal gas. If you draw a dome here, I'm just going to check it off and count the whole thing off. There is no dome. You're well out in the area where your total gas and your constant pressure lines are slightly curved up to and they're up to the right, that looks like maybe about a 30 degree, but they have a slight curvature to them. The 100 kilopascal and the 1200 kilopascal, the 1 bar and the 12 bar. State 1 is atmospheric conditions, and I don't need the temperatures here. I want them on the steam power cycle, the Rankine cycle, but here, these are all four. There's 3 temperatures here and 3 temperatures here. You're given this one. You're given 3. You could calculate these, but they're not necessary in the calculations, so I'm not going to ask you to draw. But I want to see, all right, we're coming in at state 1 atmospheric. We go isentropic is our ideal irreversible process, the 2S, straight up. The actual process increases entropy, it goes to 3. So that's a compression process, from the low pressure to the high pressure. So it goes through the combustor. We don't really show that. That is process 2 to 3, constant pressure. Temperature goes way up due to the gas being ignited. So we go to state 3, coming into the turbine. The ideal process through the turbine is isentropic, straight vertical line on the TS diagram. There's 4S. The actual cycle, it does have irreversibilities, such as friction and pressure losses and some other kind of losses that add up to give you state 4. So there's the TS diagram I'm expecting. Just want to see the state numbers, the lines drawn sort of accurately, not straight lines or anything. I mean, not with a straight edge or anything, but I can tell you know how to draw this diagram. I'm just looking for this pressure and these states, and that's about it. If you draw a dome, don't count off the whole thing. So now we need to fill in this table. So let's start. And by the way, I didn't say this is the best way to analyze these problems, is to just go ahead and get all the enthalpies. Once you get all the enthalpies figured out, the rest of it's like falling off a log, sort of. All right. And we're going to use the table values, so we will not be using the ideal gas equations very much. We'll be using the table, because the table's more accurate. So H1 is just H of 100 kilopascals and 300 K. That's on page 963. Let's go over to 963. All right, we know T1 is 300 K. Right there. Now look at your table carefully. This is H and this is U. Sometimes the U comes before the H. And there's also, we're going to be using the pressure ratio. I won't go into detail. The pressure ratio is an isentropic, it's a constant entropy property of a state that helps you analyze the entropy increase. We'll see what that means in a minute. Okay. So here's the data for 300 degrees. It goes all the way to here. And then we pick up another column with another temperature. So this is like left part of the table, right part. Let's look at 300 degrees K. H is 300.19 kilojoules per kilogram. And we used this S0 before, but we're not going to use S0. We're going to use a pressure ratio. The pressure ratio here is 1.3860, the isentropic pressure ratio. So that's all we need for state 2, but state 1, but we got to calculate 60. Shouldn't have done that. Okay, we need H2S, and if we can get H2S, we can use the isentropic pressure efficiency. I believe it was 90%, 84% to calculate H2. Well, here's how we do it. We hadn't done this before, so pay attention. We form, by definition and by design, PR2 from the table over PR1 is equal to actual pressure 2 over pressure 1. We know pressure 2 is 12 bar and pressure 1 is 1 bar. So we can calculate PR2 is PR1. We just solved this for PR2, this little ratiometric equation. PR2 is equal to PR1 times the pressure ratio. PR1, we just looked up, page 963. Here it is, by the way, PR1, 1.3860. Times 12, and we get PR2. PR2 is 16.320. So associated with that PR2 is H2S. Because these ratios are developed, assumed with the requirement of isentropic pressure ratio. So we know for state 2S, we know that the pressure ratio at state 2S is 16.32. So let's look down our table. We're looking for a pressure ratio of 16.32. Well, it's not in that column. Let's go over here. Aha, it's right between here. So we set up us a little mini calculation table, and we're gonna have to interpolate. So we have H on the left and PR2 on the right. It falls between, and you don't have to do this. I just do this to make it clear. I always do it. I find this very helpful. If you can do it in your head, fine, but I think you'll do better making your little mini table. And all comes from page 963. So here's the PR2. We have 16.28 is a table value, and that is associated with an H2S of 60702. So there's 60702. Then we have 17.30, and that's associated with 617.53. There it is. By the way, we can see the temperature here is going to be about, I'd say about 602 degrees. But as it turns out, we don't really need that temperature. We just need H2S. So we use our interpolation formula. H2S is equal to Y1 plus dy dx, y2 minus y1 over x2 minus x1 times x minus x1. And we go through this calculation. I hope I did them right. I get 610.65. So that's H2S. by interpolation and using the pressure ratios. This is only good for air or ideal gas, or in our case, air. You don't use these pressure ratios in the steam table or for water. So H2S is 16.65. Now can go through and I have H1 minus H2, AS over H1 minus H2 is the isentropic compressor formula. If you want to use H2S minus H1 or H2 minus H1, that's fine. But now the only unknown in this equation is H2. I know H1, I've calculated H2S, I'm given the compressor efficiency of 0.84%, or 84%, 0.84. So I just solve that equation for H2, and I get, hopefully I did it right, 669.79. So I've got H1, I've got H2, I got H2S, I need H3. Whoops. So let's see about H3. I've got all I need to get all I need is a temperature. I've got 1400 degrees. So I just need to go find my 1400 degrees, and I see it's on the next page. Here's 750, 1280, so 1400. Here we go. 1400 degrees. H is 1515.42. I just plop it in. Just a straight lookup. But now, okay, now I've got to find H4S and H4. I really need H4. I don't need H4S to calculate my what I've been asked to calculate, to analyze the cycle. But the only way I can get H4 is to go through and get H4S and then use the isentropic turbine efficiency equation to get H4. No other way I know to get it. Unless I use, I'm not given the N to use the ideal gas equation, so that's the only choice I got. So here's H3. Now I use the pressure ratios again. The pressure ratio at H3 is 450.5. PR3. Okay. Here's 1400 degrees K. Here's the pressure ratio, 450.5. So I use this simple relationship that PR4 over PR3 is equal to P4 over P3. PR3, we just looked up directly. PR4 now is 100 kilopascals. P4. So I saw this equation. PR4 is PR3, P4 over P3, and I get 37.541. So I know state 4 has a PR ratio of 37.541. So I look back at my table. Look like it's right between here. So it looks like that temperature, and I don't have to calculate, by the way, is about 870 degrees or so. So H4S has is whatever enthalpy that's associated with 37.541. So I have to interpolate again. I think I looked 37.541. 37. I think I looked. Did I look that up wrong? 37.35. Gosh, did I look up that wrong? 30. Oh, I'm looking. You probably saw it first. I'm in the wrong darn column. Don't do that. PR is 30. PR4 is 37.54. So it's right between these two. See, that's PR. I was looking at VR. We don't even use VR. 37. So my it lies between 37.35 and 39.27. There's those two values. That's right. There's the actual y value, the x value. And the enthalpies corresponding to that are 767.29. There we go. And 778.18. There it is. And the temperature is between 750 and 760. It looks like the temperature is about 7. We don't have to have it, but it looks like it's about what, 60. It's very close to, it's about 751 or 2 degrees. Let's look at that for a minute. So we came into this turbine at 1400 degrees and we came out at 700 and something degrees. And we need to get it back into 300 degrees before we go in the compressor. So see all that heat that's available there, 760 degree air. We're just wasting it here, getting rid of it. We're going to use that later in the combined cycle, is what I'm getting at. So now I need to interpolate for H4S. Go through the interpolation just like before. Hopefully I did it right. H4S is 768.37. It does fit between these two, so that makes you feel better. Now I take my isentropic turbine efficiency equation, H3 minus H4 or H3 minus H4S. And the only unknown there is H4. So I calculate H4 is 852.08. All right. So I think that's all the enthalpies. Yep. So now the next thing it says is to compute the power, or no. Next thing, determine the mass flow of air in the gas turbine system in kilograms per second to produce a net output power of 45 megawatts. Now, there are a couple of different ways to do that, but here's the way I chose to do it. Draw your control volume as taking in both the compressor and the turbine. You do have this work shaft from the turbine to the compressor. That's the turbine is providing work to the compressor, but since that's inside the control volume, you don't have to worry about it because it'll take care of itself. But now you do have this power out here crossing the control volume boundary of 45 megawatts. That's the net actual power output of the turbine compressor package. So now the way to analyze this is use this, you go back a little further into our first law equation. The sum of the masses times the enthalpies exiting this control volume minus the sum of the masses and the enthalpies coming into the control volume is equal to Q minus W. Well, we're going to assume this process is adiabatic, so Q is equal to 0. So the net work coming out of this thing is this work right here, 45 megawatts. And you got to put this minus. You got to be careful on the signs here. So now just start applying this equation. Well, we know even though there's a combustor, a heat exchanger between here and here, the same mass that flows through the compressor flows through the turbine. That makes our life much easier. So we end up with just, I use the mass of the air, m dot, times H exiting. Well, you have H2 exiting and H4 exiting. So that's H2 plus H4. Minus the m of the air, and that should be a dot over it. I could put this all in brackets and factor it out here, but I do later, that's fine. Now we'll look at the enthalpies entering. H1 plus H3. There you go. Now you can factor out the mass of the air, m dot air, and you have H2 plus H4 minus H1 minus H3. You know everything in that equation but mass of the air. So if you solve for the mass of the air, it's equal to the work, which right here is 45 megawatts of output work. Positive work, there's a minus sign in front of it. So if you solve for M of A, I'm not sure that shouldn't be a minus. Oh, no, I think I took care of it right here. So it's 45 over H1 plus H3 minus H2 minus H4. So it's just these H's just all plopped in. But you got to be careful on the units. Actually, they come out pretty easy. Megawatts, a megawatt multiplied by 1,000 kilowatts in a megawatt. And a kilojoule is a kilowatt. Did I get this wrong? I think I got this upside down. No. Right now that doesn't look right to me. But anyway, I got the right kilogram. A kilojoule per second. This should be down here. This second should be down here because it comes out in the denominator. So that I got the right answer. My fudge a little bit. That second should be right here by the kilowatt, because a kilojoule per second is a kilowatt, and it would come out just right here. So I got the mass airflow is 156.359 kilojoules per second. Rounded off for, for 3 significant digits for the final answer to present as my answer. And I chunked this number in memory location A. Now it says, what is the work of the compressor by itself? Well, I can just now, I didn't show it, but I just put my control volume around here. And it's just, what would it be? It'd be M of the air, H2 minus H1 equal minus work of the compressor. And I know now that I have to take the whole thing in to get the mass flow. I can't do the compressor by itself or the turbine by itself because I don't know the mass flow. But if I take both of them together, I do know their collective net output is 45 megawatts. I know all the enthalpies, so I can calculate for the mass flow. Now that I got the mass flow, I can analyze each one of these separately if I want to. So I can use that approach to find the work of the compressor actual, CA, M dot H1 minus H2, and go through those calculations. By the way, I do this. A kilowatt is a kilojoule per second. So I just stick my second up there in the denominator. It makes it easier for me to cancel stuff out or see how to cancel stuff out. And I get 57,790 megawatt, 57.790 megawatt. 57.8 is the answer to 3 significant digits. And I put that in memory location B. Now it wants to know the heat transfer into the combustor or that heat exchanger where all the heat of the cycle is input. It's just M dot times H3 minus H2. Once you got the M dot and H's, it's just plug and chug. So I get 132 megawatts. So and here's the 3 digits I put in location C. But just to look at this, I'm getting 45 megawatts of power out, and I have to put in 132 megawatts of heat. So the thermal efficiency is the work of the turbine net, or that 45 megawatts of net output power, or the amount of heat I have to put in, 34%. And that's pretty close to what the, let's go back and see what I think that's almost exactly what we got for the steam turbine. Yeah, 34.9. I didn't design it to be that way. And 34, yeah, 34.9 and 34, okay. Now the backwash ratio is just the work of the compressor over the total work of the turbine. Well, we know the compressor is 57.790. We know the total work of the turbine is equal to the work it had to provide to the compressor, plus its net output. So we get the backworks ratio is 56.2%, which means that it took 56.2% of the turbine's output just to drive its own compressor. That sounds pretty inefficient, but actually with the cost of natural gas being relatively low, it's a pretty doggone efficient process. All right, that's the second problem. Now here's the big problem. We put both of these together, and that you should have seen this coming. So here's the gas Brayton cycle here. And remember that these are about the same temperatures and everything. So we know that temperature 4 is about 760 degrees. And instead of just wasting it, we're going to now run it through a heat recovery steam generator that takes this essentially waste heat from the Brayton cycle and uses it to provide heat to generate steam for a Rankine cycle. This is a combined cycle. Very, very important. This is what is used. Almost all natural gas plants run on a combined cycle. And it just makes sense. All this hot air coming out of this turbine, let's use it as a practically free. Now there's a big capital investment required to the steam recovery generator, heat recovery generator. I'm sure it costs millions of dollars, but as far as operating expenses, once you get it done, it's just probably just a little maintenance. So we've got the Brayton air cycle, the gas turbine cycle on top, sort of the steam turbine cycle. So we've got all of these, and I use about the same values. I've got pretty much the same temperatures, pressures, efficiencies I had for the gas turbine cycle here as I had on this problem we just worked. And for the steam turbine, I've got pretty much the same property values. In fact, they are. The difference here is you can't specify how much power you get out of this one independent of this one. They're dependent because of the mixing of the heat right here. So if I'm designing this plant, I can design this cycle to give me 45 megawatts like the problem requires. But then I have to pretty much take what I get on the steam turbine cycle. As it ends up, I get about half of the power out of the steam turbine cycle as I do to the gas turbine. That's just the way the physics work out. So first thing we got to do is go through all of these equations again and get the enthalpies. But first thing, and I have these set in order. Some problems just ask you, I could just ask you the thermal efficiency and let you figure out what sequence of calculations you need to get it. But I'll give you a little help. I tell you that the output of this gas turbine is just like before, 45 megawatts. And the first thing we want to do is find the first thing we got to do is calculate all the enthalpies. And I think they've done pretty much, I didn't think of this, but I think I get the same values. I didn't think of that when I worked it out. Yeah. I could have used that as a check. I just didn't think of it. Okay. So we've actually gone through this process. It's just long. You just do the gas turbine first, and you do the Rankine second. Now, if I give it to you this way on the final exam, I would suggest you go through it again here instead of using what you've already calculated. as a check, because as you know, you get one enthalpy off, you pretty much every calculation will be wrong. But we go through the same, and their TS diagrams, they're stacked, they're the same. They just this point here is what gives you this point, but it's really the same sketch. It's just you got both of them at the same time. Let's see if I ended up with this 183. I think I didn't realize they'd be the same. Of course they're going to be the same. But again, I think you should go through the calculations to check them again. And maybe on the final exam, I give slightly, I don't remember. Anyway, so we analyze them the same way. We just do the Brayton cycle first, and you calculate the mass flow rate. And I wanted them to be the same, but it looks like I got 156 here. What did I get on the gas turbine? I got off where I got 156. Let's see what I did. Close. Not sure exactly why. I might have had an error in here somewhere. 8. I'm not sure why the difference. Let's see. It's the same properties at Avon, yeah. So got 156. Then when I did the combined here for mass flow, I'm getting off here. Mass flow. No, I got about the same thing. 156.30, 156. Maybe a digit. Seemed like I remember having one of these enthalpies wrong. I had to go back and work it. But anyway, you work it just exactly the way you do the Brayton cycle by itself. Here's where you've got to think about it. Now you're ready to analyze the heat recovery system. So you've gone through this system here and calculated the mass flow required in this Brayton cycle to give you the 45 megawatts. So that fixes the mass flow rate through here. That, in effect, determines how much mass flow rate of steam or water you can handle, because it's going to be proportional. So what we have to do, we have to analyze this system here. And the unknown we'll get is the mass flow of the steam. I put water, M of W. This M dot A up here, M dot W down here. So let's look, we've got to analyze this system right here. This is the new analysis you're going to come up with. This is pretty much already done. You can redo the enthalpies to check them, but this is new. I probably on the final, the properties are not going to be exactly the same, and in fact, you can bank on them. I'm going to give you slightly different properties where you can't just. I'm not trying to be mean. I'm just trying to give you a good test. All right. let's look. It says, compute the output of the steam. Let's see. We can do all of these. The E, I give you the right sequence you have to go through. Analyze the heat recovery steam generator to determine the required mass flow of steam in kilograms per second. So let's go to that. Here it is. No, that's the net turbine file. Here it is. So we draw our control volume, and we've got mass of air coming through here, coming in at state 4 and going out at state 5. We have mass of water coming in at state 6 and going out at state 7. They do not touch each other physically, but they're in close thermal contact such that ideally all the heat given up by the hot air is absorbed by the water, and with the right controls and the design of this steam recovery generator, it produces steam coming out, water coming in, steam coming out. So again, we use this form of the equation. It's just ideal for this. By the way, the heat transfer outside of this control volume is 0. All the heat's handling in here, but outside the control volume, there's no heat transfer, there's no work. So we use the form of the equation, the mass exiting times the enthalpies exiting, the sum of those, minus the masses coming in times their respective enthalpies is equal to Q minus W. These are both 0. So now we've got this equation. We know all the enthalpies. We know the mass of air. We calculate it. So the unknown is the mass m dot of the water. And again, be careful on your signs here. I would use this form of the equation, not go by the book. And I'll give you this equation here. I'm just going to give you in at this form, though. You're going to have to expand it. So if I expand this equation, the masses exiting. Here's one, mass of air, H5, plus mass of water, H7. So that's this thing. Now, the MH is entering. And I put it on the other side of the equation here. M dot A, mass flow rate of A, air, times H4, plus mass flow rate of water times H6. All right, that's that term. Now just solve for mass of the flow rate of the water. And units are not a problem. These units cancel out here. And I get 24.2 kilograms per second. Now I can just go hog wild and make all the other calculations. By the way, we did the pump exactly like we did. Let's see, did I get that? Yeah. Exactly the same way as we did before. And we got this 10 to the minus 3. Be careful here. And that is the work of the pump per pound, isentropic, is VdP. In this case, it's the B coming in, B9, times P9 minus P1. P9 is the last state, and P1, I'm sorry, P8, isn't it? P9, P8. Let's go look at that. No. It's P9 and P6, I'm sorry. P9 coming into the pump, P6 going out. So VdP is going to be V9, P9 minus P6. That's the isentropic pump work. You're given the isentropic pump efficiency 80%, so you can calculate the actual pump work and the actual H6. Actually, you get H6S. Yeah. And using this equation, you can calculate H6. Anyway, it's pretty straightforward. So I've got a lot of the same numbers. Now I missed this a little bit. I meant them to be the same, but I had an error. In other words, I meant, when did I come out with a mass flow of the water? 22 point, no. I came out with 24.2 kilograms per second. I meant for it to come out the same as the Rankine cycle alone in the first problem. Let's see what I got from master. Good. 22.2. No, that's megawatts. Sorry. Where's the math? 21.4 is what I meant to come out the same, but I made an error. So 21.4 kilograms on the Rankine cycle alone. And then when I put them together, I tried to get them to come out the same, but I got a little bit of difference, like 10% difference. But anyway, if you go through the calculations, the rest of the calculations, you get an efficiency. Now, the efficiency is equal to the sum of all the works, which is the work of the steam turbine, the air turbine, steam turbine. This is net. That's that 45 megawatts net output of the Brayton cycle turbine. Here's the 25. That's the net output of the steam turbine. And here's the work of the pump, 0.244 megawatts. Here's the heat we put in the combustor now. It's just the heat of the Brayton cycle. We don't put any heat in that's the whole magic. I always say magic, the advantage of this cycle. The only heat we have to pay for is here. We get this free. So the efficiency is just the work out, the net work coming out of here, the net work coming out of here, minus the pump work over the heat we put in here. And if we calculate that, instead of 34 or 35%, by virtue of using that waste heat, we get 53.1%. And I wrote this down just to compare. The Rankine alone was 35%. Brayton alone was 34%. Put them together and you get 53.1%. Pretty good deal. All right. So remember, on the final exam, I'll give you I think I'll just give you a combined cycle. I'm not going to work you to death. I'm going to give you a combined cycle. The numbers will be different. You'll have to go through this full analysis. Okay. All right. Here's the last problem. This is a heat transfer or a heat pump. And this is a real world problem. I may not have the parameters right because I took it off an article I read about what Tesla was doing, and Elon Musk was all excited about this heat pump that his engineers had come up with. And it is a pretty novel application of a heat pump in a battery-powered vehicle. In a battery-powered vehicle, you think of it in an internal combustion engine vehicle, the heat to heat your inside the car is pretty much free. It's produced by the engine combustion process, and all you got to do is control it and route it the same way. It doesn't cost you hardly anything. But in a battery-powered vehicle, it's different. That heat, it can be, if you just generate it from electrical resistance heat, it takes a lot of power. And you can't get enough of, generally you can't get enough heat out of your electronics to heat your cabin. So it can be a problem. All right, let's read this problem. And I made up some of this stuff, but the overall, it's, what do they say on a movie that's based on true events? Tesla is developing a heat pump to heat the inside cabin of a new model battery-powered vehicle. The novel use of the heat pump will be to heat the inside of the cabin in cold weather while simultaneously providing cooling for the 90 kilowatt-hour battery pack. As you know, all the energy for this vehicle comes from the battery pack. You hook it up to a charger and charge it up to 90 kilowatt hours of power, and you go like 300 miles or so. The calculated heat loss from the cabin at one critical design point, that's the design point we're using, is 1,200 BTUs per hour. It's actually a ton of refrigeration. So that's how much, say it driving 80 miles an hour in a cold weather, that's how much heat you need to pump in that cabin to keep the driver and passengers comfortable. The refrigerant is R134A. As shown in the figure to the right, the evaporator and condenser pressures are. So here's what we're trying to do. We're trying to heat the cabin. And if you look at the tables, you'll see you need a high pressure of the 134A to get it hot. So need about 100 psi, 100 pound for square inch in the condenser pressure. Down in the evaporator, you need a pressure of about 50 pound force per square inches, and that's given in the problem statement. Now, while the vehicle is operating at this design point, the heat load from the battery pack is 2,000 BTUs per hour. So what you're sort of trying to leverage what you got here, you need to design it to heat the cabin because you want to keep your passengers comfortable. So you need the 1,200 BTU. You need a maximum capacity of 1,200 BTUs per hour. But why not, while you're doing that, take some of the cooling you get as part of the vapor compression refrigeration cycle, use it to cool your electronics. Now the electronics I calculated will probably need about 2,000 BTUs per hour, not near as much. Okay. So we got the battery pack down here in the cold area of the cycle, and we got the inside of the cabin up here at the hot area. We got a compressor efficiency of 80%. This is really important because this battery pack has to power this compressor. So we don't want to drain our battery heating the cabin. That's the whole idea of this heat pump. So the first thing it says, look up and calculate all the relevant enthalpies and place them in the table to the right. Sketch the TS diagram. Determine the mass flow of refrigerant. Determine the actual battery power through a suitable electric motor to drive the compressor. We know that the compressor has to be driven by a small electric motor that's powered by the battery pack of the vehicle. All right, it says, what would the electrical load be on the battery pack to provide 12,000 BTUs of heating using electrical resistance heat? We'll calculate that. Calculate the cooling capacitor of the evaporator. This is the cold part. And used to simultaneously cool the battery pack electronics in BTUs per hour. Does the evaporator have enough cooling capacity to handle the heat load of the battery pack? And then it says calculate the COP of this device operating as a heat pump. Then we go on. Calculate the COP beta of this device operating as a cooling device. So it's 2 in 1. Now, here's a TS diagram. It's not complicated. This is refrigerant R134A operates under the dome and outside the dome, 2 phases, liquid, vapor, and a mixture. So there is indeed a dome involved, just like with steam. And we have 2 pressure levels here. High pressure, as seen, was 100 psi. There's a high pressure, 100 pounds per square inch. Low pressure is 50. Now here are the temperatures. If you look in the, all right, let's go to R134A in the English. Let's see, that's going to be toward the end, 1019. Oh, I've got the pages here, dummy. I've got the pages. Page 994 or so. All right, there's R134A. And why did we pick a pressure of 100 PSI as our design pressure? Well, look over here. Here's 100 PSI. What's the temperature at 100 PSI? 80 degrees Fahrenheit. Is that enough to warm a cabin? You generally want about 70, 72, 73. Yeah, that ought to be plenty. You want a little higher temperature because you're transferring temperature from the hotter heating coils of the heater into the passenger side. So that's why we chose. We might have should have went a little bit higher, maybe to 120, but we chose 100 degree PSI. That gives us about 80 degrees temperature. And actually, if you look at the table, it's 79.17 degrees. And I want you to write that on there. You could write it right under here, or you can write it right over here. Now let's look at the lower temperature. We want to cool the electronics. Well, what kind of lower temperature? Well, if we get the electronics to about 50 degrees Fahrenheit, what is that? That's about 10 degrees C. That's plenty cool for electronics. We don't want to freeze them. So let's look over here. We 50 PSI, we've got about 40 degrees Fahrenheit. That's a nice cool temperature for the electronics. So that's the way we set our pressure. Now, and you don't have to do this design. I've already done it for you, but that's where I got the pressures. Okay. Now let's start getting the enthalpies. H1 is a gimme. It's saturated vapor at 50 PSI. Here's 50 PSI R134A. We want HF 24. What am I doing here? I'm sorry. It's getting low. We want HG, H of gas, saturated vapor, 50 PSI, HG 107.43. 107.43. But now we don't have to go through the same method to get H2S. So we want to look and see what S1 is, because it's going to be the same S up in this area. S1 is S of G at 50 PSI is 0.2189. There it is right there. So how do we get H2S? Again, if we know H2S, we know our compressor isentropic efficiency is 80%, so we can get H2. H2 is what we need. Well, we know, what do we know about state 2S? Well, we know it's 100 PSI. And we know its entropy is 0.2189. So let's look, let's go to our mini table. We know we're out here in the superheated area. It's all vapor. So we're looking for 100 PSI mini table. There it is. And we want the entropy to be 0.2189. 100 PSI, 0.2189. It's almost right at the top of the table. So let's pull out our table we need for interpolation. So we're between 2173 and 2265. There we go. And the enthalpy, and be sure you get in the right column. Entropy is the next to the last. They'll switch it on you now. So the entropy at this 112.68, there it goes. 117.73. There it goes. We put a little y we're looking for. We're looking for this interpolated y, which is h of 2s. And use this formula that h of 2s is equal to h1 plus dy dx. Y is h, so it's 117.73 or 112 minus 112.68 over 2265 minus 2173 times the actual s times s1 at state 1. We get h2s is 113.56. Now we can use our isentropic compressor efficiency formula. We know it's the isentropic compressor efficiency is 0.8. The only unknown in this equation now is H2. So we solve this equation for H2 and we get 115.09. So that's H. We've got H1, we've got H2S, we've got H2. H3 is a gimme. H3, and I think I tell you up here, saturated liquid at 100 psi. This is constant pressure. P2 is equal to P3 is equal to 100 psi. Be sure and read these little notes carefully. So I know H3 is just a straight lookup at 100 psi. What page is that on? 994. $994, 50p, no, 100 psi, sorry. We're looking for HF, which is H3, HF fluid, 36.99. There it is. And the nice thing about a refrigeration circuit, we know H3 is equal to H4. So we know what H4 is. There it is, 36.39. Now we need to find the mass flow rate. So when it tells you to analyze the condenser, we know what heat transfer we want is 1200. That's the design point. Out the hot part, the condenser, and that's heat transfer out, so it's negative. I like to use the correct signs, H3 minus H2. If you use the book, you would get plus 1200 and you would get over plus, these two would be reversed. That's fine. You don't get the right answer. If you get a negative case flow, you need to stop and look at your numbers and see if everything's okay. It might be you just got one side, a minus on the bottom and a plus on the top. Should have had a plus on both, a minus on both. Probably what it means. Just make sure you're okay with your numbers. Go through the calculations and you get the mass flow rate is 0.0427 pounds per second. Now you can go to the compressor and you can figure out how much power the compressor needs. The work of the compressor is m dot times H1 minus H2. And there's your mass flow rate. I stuck it in memory location A and kept all of these decimals. For the actual answer, I just put, for the box answer, I put 3 significant digits. Here's my enthalpies, H1 and H2. There's a little bit of a conversion here. Mass flow is pound mass per second. Enthalpies is BTU per pound mass. I have this conversion factor in my conversion sheet that 1 kilowatt, it actually says 1 watt is 3.413 BTUs per hour. So I just in my head say that, well, 1 kilowatt is 3413 BTUs per hour. And the BTUs per hour, I stick the hour up here to make it easier to see what cancels. And I get the work of the compressor is minus 340. And now if you get a plus here, I'm okay, as long as you got the right numbers. I get 0.345 kilowatts, which is 345 watts. Whoops, I didn't circle that. Now he says, well, how much, that's how much watts I would need to drive the compressor, 345 watts. Now, what if I used electrical resistance heat directly from the battery? Well, I have to just convert the amount of heat I need in BTUs per hour in kilowatts or watts. And I use the same conversion here. It's real handy. And I get 3.52 kilowatts. So if I were going to use electrical resistant heat, I'd have to take 10 times as much power out of my battery as I'm doing with a heat pump. That's why it's so advantageous to use a heat pump. Now, there's a lot of different operating conditions in a vehicle, and the battery pack and your environmental control system's got to handle them all. But you've got to design it to handle the worst case situation, to make sure the physics is there to do the worst case. And then you have got to have a good control systems and valves and so forth to get the right amount of heat to the right place where you need it. Now let's look at, do we have enough cooling capacity on the cold side, the evaporator side, to simultaneously cool our electronics? Well, electronics only need about 2,000 BTUs per hour. Let's see how much we got. Well, if we do the evaporator, m dot times H1 minus H4 equal the Q dot of the evaporator, or the Q in. It's sucking heat in, cooling. It's cooling, which I like to think is sucking heat in. So there's our mass flow, same mass flow through the whole system. Here's the enthalpies. Convert it to hours, and we get almost 11,000 BTUs per hour. Is that enough to provide 2,000 BTUs per hour? Of course it is. So we got way extra cooling that we just dump overboard, or probably some other use for it. But we had to design our system to give the heating we needed. And we sort of got this 2,000 BTUs hour of cooling. Now we got too much cooling. We can't let it all go into the electronics, or we'd freeze them. I don't think electronics actually do work okay, but I don't know what temperature that would give you. That might give you, well, the air temperature is just going to be 40 degrees or whatever, 50 kilowatt, 50, that's 40 degrees. So I don't think it hurt a thing to dump all that cool air through your electronics. It's not going to change the temperature. It's going to be 40 degrees. It's just going to cool them down to 40, and that's all it's going to do. So I don't think you need to worry about the excess heat. But if you didn't have 2,000 kilowatts, you wouldn't ever get it down to the cool temperature that you desire. All right, that's it. This has been long enough, so I'm going to sign off. Now, if you have any questions about this, I'm going to tell you what, on the final, you're going to have a combined cycle to analyze. You're going to have a heat pump, very similar to this one to analyze. You also, I haven't covered it, but I wasn't satisfied with the way you guys converted kinetic energy, velocity squared, which is meters squared per second squared, into the two types of units we use. That's in the metric system. You want to end up with kilojoules per kilogram. And in the English system, BTUs per pound mass. And I may very well sneak in a problem, about a 10-point problem, where you have to convert velocities into those velocities squared, kinetic energy. And so you better learn how to do that. I'm not going to give you a sample problem. That's ought to be pretty short. We had to do it on a test, so you can go back and look at your test. All right, that's it. Hope stay safe. Don't get sick. And touch base with me if you have any questions. I hadn't heard from any of you guys. I hope y'all look at the videos. I know that the quality is not that great. I understand. And they're long. I know. Got a lot to do. I know. But I want to see you make a good grade on this file. Again, it's, unless I misread something, it's Tuesday, May the 5th at 8 o'clock. I will give you the formula sheets and the test itself somewhere around 7:30, give you time to print it out. and I want it back by noon, which gives you probably 3.5 good hours to work on it, because you'll have to scan it back in some way and send it back to me. But I don't want you to work over it over that amount of time, because you got a lot of other stuff. Anyway, stay safe, stay well. I'm signing out.